Oh, hi everyone, my name is Max Leamy, and today I'll be presenting the constant velocity lab, the first lab we completed. Okay, so just as an introduction, in this lab we recorded an object with constant velocity and direction, then tracked the displacement of the object and compared the results with a computer model representing perfectly constant velocity. And that was the video that I recorded. Okay, so for the physics concepts for this lab, Newton's first and second laws are used heavily in the experiment. Newton's first law states that if F net on an object is equal to 0, the object will maintain constant velocity. Newton's second law states that change in velocity is related to net force, mass of the object, and change in time. Two models were used for this experiment. The model on the left represents the experimental model. For this model, I created a coordinate system and tracker to represent displacement of the ping pong ball and measured the x-coordinate of the ball at each frame of my video. The right is the computer-generated model, which generates the position of the object over time if velocity is perfectly constant. For the experiment, I recorded a ping pong ball rolling across the wall of a pool table. To track the ping pong ball's displacement, I created a coordinate system and tracker that positions the x-axis along the center of mass of the ping pong ball. I then created a reference distance of the ping pong ball's radius to ensure my displacement results were accurate. Then I measured the position of the ping pong ball during each frame of the video and plotted the results. To find the initial velocity of the ping pong ball, I subtracted the position vector of frame 1 from the position vector of frame 2 and divided by the change in time of one frame of the video. To code the computer model for the experiment, I first added the mass of the ping pong ball into the code and set the delta t equal to the time between one frame of my footage. I then set the maximum time t to 1.468 seconds, the amount of time I recorded the ball's displacement in the footage. Finally, I added the initial position vector and initial velocity vector to the code and set the fnet vector equal to 0, 0, 0. Setting that force equal to 0, 0, 0 ensures the computer model produces a position versus time graph with a constant slope, or in this case, velocity. For the discussion, I plotted the x-position results of both the computer model and the experiment over time. The computer model data has a constant slope throughout the entire time measured, indicating it shows what the position versus time graph would look like if the ping pong ball had a constant velocity. However, the experimental data has some variation in slope throughout the experiment. As time passes, the magnitude of the velocity for the experimental data decreases and becomes more positive, indicative by the change in the slope. This result indicates that the ping pong ball in the experiment experiences a net force in the opposite direction as the motion of the ball. From the graph, we can also determine that the experimental data is closer to accurate from a small delta t than a larger one. As time increases along the graph, the gap between the position of the ball measured during the experiment and the expected position of the ball based on the computer model gets larger and larger. Some of the discrepancies between the experimental data and the computer model data could be due to error. The first source of error is human mistake. I might have made mistakes using tracker to find the center of the ball in each frame, setting the reference distance for the experiment, and I may not have kept the camera completely steady. Another source of error is the ball could have experienced a net force during the experiment that causes its measured positions to deviate from the expected ones. In conclusion, from this experiment we learned that we can track the motion of an object in tracker relatively accurately. If the axes of the coordinate system for tracker were flipped, the graph would have an opposite slope. We can also determine that the ping pong ball must have had a net force during motion that decreased the magnitude of the velocity vector. We cannot know exactly what each component of the net force is from Newton's laws, but we can calculate the magnitude of the net force vector. Finally, we learned that our model and Newton's laws can be used to predict changes in velocity and position over a small delta t, and that these calculation methods become less accurate over time. Thank you for watching my presentation. I hope you enjoyed.